Hello everybody, we are discussing about the yield surface in case of 3-dimensional problem. So, once we theoretically assume the functional form of yield surface, and then we can see that how this functional form can be derived in this particular case also in this particular situation. And then to do that, maybe some assumptions are required to reach certain functional form that will predict the yield surface in case of the 3-dimensional thermomechanical problem. So, in general, so first we assume that already seen that this functional form is as a function of all the individual stress component, all the normal stress and the shear stress components, or explicitly we can say that it can be a function of only the principal stresses sigma 1, sigma 2, sigma 3, because sigma 1, sigma 2, sigma 3 itself can be represented in the form of the original or initial state of the stress. To do that, we assume this is the functional form. Now, for isotropic material, we understand that if we assume the isotropic material, the properties are same irrespective of the any direction. So, it is possible to write in terms of the principal stresses. That means, for isotropic material, then this it's a all this directly we can convert the initial state of the stress, the original state of the stress, in the form of principal stress if we assume the isotropic material. That means, in terms of the principal stress, that this cubic equation to find out the root of the equation or to find out the principal stress components, that we express this equation like that we have already discussed, that we can express from the state of the stress in terms of the principal stress. Also, this cubic equation can be represents, and the roots of the cubic equation is the represents the principal stress components. So, now from this cubic equation we can say it is a in terms of the stress invariant I1, I2, I3. If we put the appropriate value, in this case we will be able to reach this thing, that sigma minus lambda 1, sigma minus lambda 2 and sigma minus lambda 3, such that this lambda 1, lambda 2 and lambda 3 can be the roots of this particular equation. So, in this form, now once we reach this form, then it is true. That means, once we representing this yield functional form in the form of a principal stress, it means that we are assuming the isotropic material case. Now, we know the stress invariance can be expressed in terms of the principal stress as well, also I1 sigma 1 plus sigma 2 plus sigma 3. Similarly, I2 in the form of a sigma 1 sigma 2, sigma 2 sigma 3 and sigma 3 sigma 1 in that form, and I3 equal to sigma 1 into sigma 2 into sigma 3. So, these are the stress invariants in terms of the principal stress components. Now, this for isotropic material, K is the functional form, this particular K decides the shape of the particular form of a function. So, F this K can be represented this functional as a function of I1, I2, I3, or K can be represented as a function of sigma 1, sigma 2, sigma 3. It means that this functional form can be represented in the form of either principal stress or in the form of a stress invariance. That stress invariance itself is a function of the principal stress value. Now, if you want to very high accuracy, in that case plastic deformation is pressure independent. That we already explained this thing, that any state of the stress can be divided into the hydrostatic stress component and the deviatoric stress component. But if we assume that plastic deformation is independent of the hydrostatic stress component, then we can reach some conclusion from here also. So, solids, because solids under hydrostatic pressure do not deform plastically, we normally assume the solid under hydrostatic pressure is basically the elastic deformation is there. So, therefore, once we consider the plastic deformation, we can reduce the stress variables. For example, we know the hydrostatic stress component, the principal stress component, and the actual value of the principal stress minus the sigma h. Sigma h is the hydrostatic stress component. Similarly, sigma 2 d indicates the deviatoric stress component is the state of actual value of the principal stress minus the hydrostatic stress component. Similarly, for sigma 3 d also we can represent the sigma 3 minus sigma h, and we know that hydrostatic stress component is just simply average of this value sigma 1 plus sigma 2 plus sigma 3 divided by 3. So, this is the hydrostatic stress component. Now, if you represent the instead of that stress invariant I1, I2 and I3, that we can represent this, if we assume that plastic deformation is independent of the hydrostatic stress component, then we can represent this functional form the stress invariant of the deviatory component. But if you look into the stress invariant for the deviatory component I1d, is simply this first stress invariant in the deviatory components, that is equal to 0. If you put this value, in this case maybe sigma 1 d equal to sigma 1 minus sigma h, hydrostatics component. Similarly, sigma 2 d sigma 2 minus sigma h, and sigma 3 equals sigma 3 minus sigma h. It means that sigma 1 plus sigma 2 plus sigma 3 minus 3 sigma h, and we know that sigma h itself, value of this value sigma h equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So, from here we can see that it becomes 0. It means that deviatory first stress invariant, but in terms of deviatory component it becomes 0. So, that we can further simplify this functional form. We can say that this functional form, that K in isotropic for isotropic material, and if we assume that plastic deformation is independent of the hydrostatic stress, then K can be represented, this functional form can be represented as a function of the two other deviatory component, the I2D, the deviatoric stress invariant, I2D in form of, and I3D, it depends on this. Now, further if we look that for isotropic pressure independent material, K can be represented, this K can be the functional form, K is equal to function of I2D and I3D. Now, plastic response of materials often observed to be nearly the same in tension and compression, but in normal engineering material, if we consider that deformation behavior, that means yield point for tensile and compressive more or less almost same. So, from that point of view, we can see if we assume that yield point for tensile and compressive load is same, it means that if we are neglecting the Bausinger effect, that means if there is no Bausinger effect, meaning that the yielding happens at the same point irrespective of whether it is tensile load or compressive load. So, therefore, if we assume no Bausinger effect, in that mathematically we can say that no Bausinger effect means that it is having the magnitude is the same irrespective of tensile and compressive load. Mathematically we can see that I2D sigma ij, that means second or third, this I2D means this is the two both stress invariant should be independent of the sign, that means I2D sigma ij should be equal to I2D equal to minus sigma ij. Minus sigma ij means just simply changing the magnitude of the stress from tensile to compressive or compressive to tensile. So, then it should be same, that means then it represents that it is independent of the sign, that means whether it is plus or minus, what we represent the tensile load or tensile stress as a positive and a compressive load as a negative. So, once you do that, then it should satisfy these two equation. So, therefore, similarly I3D sigma ij should be equal to I3D minus sigma ij, that means it is independent of the sign whether it is plus or minus, that means independent of the whether it is tensile load or compressive load. Now, must ensure that F is an even function of I3D. We can see that we have seen that I2D and I3D, then that means second stress invariant and third stress invariant. We can see that if we change the sign of the sigma 1 and sigma 2 and sigma 3, that means sigma 1 equal to minus 1, sigma 2 equal to minus sigma 2 and sigma 3 equal to minus sigma 3. In this way, if we change the sign, then the expression of the I2 does not change, it remains the same. It means it is satisfying this functional form, but if we change the sign of the sigma 1, sigma 2 and sigma 3, in that case, then this I3 is basically there is a change of the sign for in case of the I3. It means that F is not indicates that F is the odd function, that means it depends on the sign convention. It means that thus depends on the sign convention means irrespective, that means it if we does not consider that means it does not satisfy this this condition of no Bausinger effect. So, therefore, we can eliminate Bausinger effect by simply ignoring the I3D altogether, that means we can simply ignoring the I3D. That means we can eliminate the Bausinger effect, because if we consider the I3D, that means we have to consider the Bausinger effect. Then even if we consider only the I2D, then in that cases there is no Bausinger effect. Mathematically we can see that it should be some even function, and that is satisfying. So, therefore, if we consider the isotopic properties or isotopic material pressure independent, that means yielding is pressure independent, and if there is no Bausinger effect, then we can say the functional form can be further simplified as the K equal to only function of I2D, that means it is a function of the deviatory component of the second stress invariant. Now, once we get this expression, I to d, we can see the find out the I to d. I to d is simply minus of sigma 1 sigma 2. This is the deviatory component, sigma 2 sigma 3 deviatory component, sigma 3 sigma deviatory component. Now, if you put this value of manipulation of this thing, that deviatory sigma 1 d equal to sigma 1 minus sigma h, similarly sigma 2 d equal to sigma 2 minus sigma h. So, like that if we put all this value sigma 2 minus sigma h, in this case sigma 3 d equal to sigma 3 minus sigma h. If we put all this value and replacing the sigma h equal to 1/3 of sigma 1 plus sigma 2 plus sigma 3. So, in terms of sigma 1, sigma 2, sigma 3, we can represent, that means in terms of the principal stresses, the I to d can be expressed in this particular form, that 1/6 this common to all, that sigma 1 minus sigma 2 square, sigma 1 minus sigma 3 and sigma 3 minus sigma 1 square. So, therefore, k can be represented in this form if we ignore this constant term, because constant depends on the other depending on the particular condition. We will see how constant terms can be vary depending upon the loading condition, that means whether it is pure shear, biaxial state of the stress or only uniaxial tensile. So, all these cases this constant can be valued. So, finally, we are getting the functional form particular shape, this function this functional form is that this particular k equal to sigma 1 minus sigma 2 square, sigma 1 minus sigma 3 square and sigma 3 minus sigma 1 square. This is the typical functional form. Irrespective of that, constant term can be derived depending upon the loading condition, or this can be represented in other way also, that in terms of the initial state of the state, that means sigma 1 1, sigma 1 2, and so that means in these cases this here it can be represented in the form of all the normal stress components as well as the shear stress component, or this functional form can be represent only the principal stress component. So, therefore, the factor 1/6 included into the in terms of the arbitrary constant. So, therefore, this functional form is well known von Mises yield function that we normally use during the simulation also. In finite element simulation, we assume that the plastic deformation or equivalent stress that follow in the von Mises yield criteria or von Mises yield functional form we normally consider. So, in this case, but remember, once we reach this particular expression, we have to remember the what are the assumptions we consider. First, this is true in case of if we consider the isotropic property, isotropic material property, these things, and we are assuming there is no Bausinger effect. That means the yielding of tensile and compressing is the same value, and then it means that there is no Bausinger effect, and the plastic deformation is independent of the applied pressure. So, that means plastic deformation we are considering only the because of the deviatory stress component, not the hydrostatic component. So, therefore, once we with this all assumption we can reach this is the functional form of a von Mises yield function. Now, we can look into this thing. So, isotropic we can check back also that whether this condition this expression or particular functional form of the von Mises yield function is satisfying all these criteria or not. So, isotropic, that means retaining the principal stresses, and the each principal stresses enters equivalently. If we look that sigma 1 minus sigma 2, this is the expression, and sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So, all this term actually enters equivalently, that means enters equivalently in this particular expression. So, k equal to, for example, this is the functional form. Pressure independent, that means if we simply add the pressure, adding the constant to the principal stress component does not alter the functional form. So, therefore, we can say that it is also satisfying the pressure independent. For example, if you say that sigma 1 can be replaced by if sigma 1 or something minus sigma h, something like that. So, similarly sigma 2, sigma 3 also, that means we adding the constant term with the principal stress does not change the functional form. So, therefore, it is satisfying this condition also. No Bausinger effect. The sign of the stresses does not alter the function. If you change the sign of the stresses, then sigma 1 to minus sigma 1, sigma 2 minus sigma 2 and sigma 3 to minus sigma 3, then it does not change the functional form. Therefore, all these three conditions are satisfying for this particular von Mises yield condition. And we also graphically represent this, for example, this sigma 1, sigma 2, the principal stress axis system. In this case, we are make one line in such a way that this particular vector makes the equal angle for with respect to all the principal stress axis, and along this line it is representation of the sigma 1 equal to sigma 2 equal to sigma 3. So, this indicates the yield surface and it represents the cylindrical this thing. So, yield surface, and we can see also. So, this is the original state of the stress, and we can see that actual state of the stress is the yielding occurs. It consists of the this part both the this thick deviatoric and the hydrostatic component, the state of the stress, but this hydrostatic component does not change alter the yield functional form. Now, if we consider the two dimensional problem, two dimensional yielding curve for the plane stress plasticity problem, sigma 3 equal to 0 in this particular form, that means k equal to, say we start with the sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Now, in this functional form, if it is two dimensional problem, if we assume that plane stress problem sigma 3 equal to 0, then k can be represented like that, sigma 1 minus sigma 2 square, sigma 1 square plus sigma 2 square. So, in two dimensional problem. Now, in two dimensional problem, if we see the uniaxial tensile testing, if we apply this thing uniaxial tensile testing, it indicates that sigma 1 equal to sigma bar. So, sigma bar is the uniaxial tensile testing, indicates, maybe we can say that this is the yield point for the uniaxial tensile testing. The sigma bar is the yield stress value of a particular material. So, that means the principal stress is only sigma 1, there is yield stress value sigma bar, sigma 2 and sigma 3 equal to 0 in this particular cases. Now, if we put this value here in this expression, then we can reach the k is equal to 2 sigma bar square, or otherwise sigma bar is equal to root over of k by 2. So, we can reach some expression of sigma bar, or we can reach some expression of the k also in this case. Now, if we consider the biaxial tension, the principal stress value is the same, sigma 1 sigma 2 equal to sigma bar and sigma 3 equal to 0. If we put, then we can reach also the same value, sigma bar equal to k root over of k by 2. But in case of the pure shear condition, suppose we are making some sample experiment that where we are following the simple shear condition, shearing happens. So, in that cases, the principal stress sigma 1 equal to minus sigma 2, or sigma 2 equal to minus sigma 1 and sigma 3 equal to 0. Put this condition here in this expression, then we can reach the sigma bar is the equal to root over of k by 6. This sigma bar indicates the value of the shear yield point value, or shear yield stress value. So, we can see that this particular expression, this k equal to this functional form, can be represent kind of the ellipse in this case, and on this ellipse, that this line indicates that major axis of the ellipse, along the major axis of the ellipse is equal to sigma 1 equal to sigma 2 in the along this axis. We can reach the different point also in this point, the in case of the biaxial the sigma 1 equal to sigma 2, then this is the this value biaxial state of the stress, it represents the root over of k by t. But if the uniaxial, then only sigma 1 equal to sigma bar in this case, then we can reach the root over of k by 2, because this is uniaxial, that means stress is along the one direction. It is the pure shear condition, then sigma 1 equal to minus sigma 2, or sigma 2 equal to minus of sigma 1. So, pure shear condition, it can lie in this particular point, and here also root over of k by 6. So, that this different cases, we can see the major to minor axis ratio is basically root over of 2 by 3. So, it means that once we know this functional form, then we will be able to know that what is the value of the constant, in such a way that if you conduct the uniaxial tensile testing, in this case the uniaxial tensile testing, the sigma bar is maybe known, then we can change this function is sigma bar is known, and k is the twice sigma bar square. So, we can say if we replace in case of the twice sigma bar square equal to sigma 1 minus sigma 2 square plus sigma 1 square plus sigma 2 square. So, in this case, this is the functional form, but in this functional form, this sigma bar is known quantity, and this sigma bar indicates the value of the yield point. So, that normal that value of the yield point, but with the application of the normal stress value. So, normal yield point value sigma bar indicates. So, this is the known value for a particular material, and we can use this functional form, this particular functional form to define the yield surface in case of two dimensional problem. Similarly, suppose the experiment can be conducted on the pure shear condition. So, pure shear condition, then this constant value can be different, or we can say that it k is the, in this case the k equal to 6 sigma bar square. So, in this case, if we replace this sigma bar square like that, also if we replace this k equal to 6 sigma bar square. So, this expression can also be used, that also predict the yield stress value or yield surface or maybe yield curve, but in this case this sigma bar is measured, this is the shear yield point value. The shear yield strength is different from the yield strength which we measure in the application of the normal uniaxial tensile testing. So, that means this value depending upon the experimental condition, this constant term can be defined depending upon the whatever the experimental condition we are following, whether we are following the pure shear condition and we measure the only the shear yield point yield strength, or normal yield strength we are if we consider in case of the uniaxial tensile testing. So, depending upon that this constant term can also vary. Therefore, this constant term k other way, because we represent this is the functional form equal to k, and k can be defined depending upon the experimental condition or value of the yield strength value measured and different situation. So, now the constant k determines the size of the yield surface, it is the size of the yield surface as opposed to the shape. K actually decides the size, but shape is already decided this by this equation. This equation decides the shape of this particular curve, but size is decided what value we are considering a k. Now, physically k represents the hardness, and harder material requires the largest stresses to undergo the first plastic deformation, and after the first plastic deformation then we can consider the strength level depending upon the this strain hardening parameter of this particular material. So, now this other way also we can represent this functional from that equivalent or effective stress value to the yield surface as an isostate surfaces. So, for example, representing all the combination of the stresses that represents only in case of the elastoplastic transition. For example, this is the one isostress line. So, in this case it can be corresponds to the one uniaxial tensile testing, this is the sigma value and this is the strain value. So, suppose this is the yield point. So, then this corresponds to can be the sigma 1 bar. So, then when it is the yield point, first yielding happens at particular point sigma 1 bar, and this represents the isostress surface, and this surface can be represented in the form of a this von Mises function form. If it is a two dimensional, we use the 2 dimensional form. If it is 3D, we use the 3 dimensional form. But this is the representation of this thing. For example, although we are talking about the functional form, this is the von Mises yield function for the for example uniaxial tensile testing, the sigma 1 equal to sigma bar, sigma 2 sigma 3 equal to 0, then we reach the k value is equal to I sigma bar square, and sigma bar square equal to half of this. So, this is the von Mises yield function in case of when the sigma bar is measured in case of the normal yield strength value. Now, this normal yield strength value, this is the functional form, this is the functional form in this case. So, therefore, this curve is represented by this equation, and in this case the first yielding happens sigma bar. Now, for example, after straining after strain harden, the material becomes strain hardened, the yielding point shift in this particular sigma 2 bar in this case. Similarly, after strain hardening it can reach the sigma 3 bar. So, in this case all represent the isostress surface that corresponds to the same functional form sigma 1, sigma 2, sigma 3, but this is changing, or we can say the k value is actually changing, and that takes care of the strain hardening effect, and that evolve the yield surface in this particular by looking into the effect of the strain hardening during the deformation process. So, therefore, in this way we can represent the von Mises yield function, and we can predict this plastic deformation following that plastic deformation such that this either yield curve or yield surface follow the equation of the von Mises yield function. Now, once we predict this is the yield surface by following in maybe von Mises yield function or maybe some other functional form also, but in general we consider the von Mises yield functional form. If we predict this form, the yield surface it predicts, by yield curve it predicts. Then normality condition or flow rule is important, because what way the plastic deformation will sustain during the further deformation process. Sometimes we can use some kind of the flow rule to just represent the flow potential function in this particular. For example, this what way the yield surface evolve. So, initial yield point we can define, and that may be equivalent to the what is the uniaxial tensile testing data. From there where the yielding start, that yield strength can be equal to this. But what it evolve from this point to the yield surface evolve from the next point, that can be governed, controlled by following some kind of the flow rules, or it should maintain the normality condition during this process. So, therefore, during yielding the ratio of the resulting strains depends on the stress also, because strains, the resulting strain also depends on the state of the stress that causes yielding. So, the general relation between the plastic strains and the stress states are called the flow rule. So, what way we can represent the plastic strain and the stress, how they relate, that we can represent in the form of a flow rule. For example, in this particular case, this d increment of the strain, incremental strain is a d lambda is a constant, we can say sometimes the plastic multiplier, and it depends on the stress. The del f basically represents the yield functional form, and del f by del sigma ij. So, now if we assume that this functional form can be represented like that, sigma bar square equal to this, and then we can say that the increment of the strain d epsilon 1 can be this, we can do this simply derivative of this f functional from f equal to, in this case the f functional from equal to sigma bar square, and that is equal to in this case half of square sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square, and that is the half. So, this is the functional form. Now, from this normality condition, if you see the plastic multiplier, and then from there you assume this is the functional form, and here if you see the del sigma bar by sigma 1, then we can see, we can reach this expression. Similarly, and then finally we can reach this expression twice sigma 1 minus sigma 2 minus sigma 3 into d lambda. So, this incremental of the strain depends on the principal stress value as well as the depends on the plastic multiplier, that means d lambda. This is the constant term, this what value depends on this value. Similarly, d epsilon 2, d epsilon 3 is function of the other stress parameter and this ratio. So, such that during the deformation we can assume the material volume remains unchanged. It means that it maintains the continuity also, that means d epsilon 1 plus d epsilon 2 plus d epsilon 3 should be 0, and that once we maintain this condition, then we can reach the different expression of this thing, or sometimes we are interested to know what are the stress ratio it should maintain for the to avail the some kind of incremental during this deformation. So, here suppose the incremental strain is d epsilon, this direction of d epsilon is independent of the incremental d sigma, that means which direction d sigma is moving. So, this increment of the strain is independent of the direction of the stress, and d epsilon is a vector normal to the yield surface f. So, therefore, this is, if this is the yield surface, the d epsilon can be considered as a vector form and which represents the normal to this surface, and d lambda is the arbitrary constant. So, that constant has to be decided when we try to analyze all these things. So, therefore, this flow rule or normality, this flow rule actually decides what way the yield surface will evolve, and for a particular increment of the strain value, and what way how this increment of the strain is it depends on the stress magnitude, but it is independent of the direction of the stress value, and then you have to decide what may be the, it also depends on the this plastic multiplier d lambda. So, depending upon the analysis problem, d lambda can be decided. Okay, let us look into this uniaxial tensile testing in x1 direction. So, here we can see that sigma 1 equal to sigma 2 and sigma 3 equal to 0, that we know in case of the uniaxial tensile testing. So, therefore, we can express the d epsilon 1, d epsilon 2 and d epsilon 3 in terms of that, because sigma 1 suppose principal stress value equal to sigma that is the results from the uniaxial tensile testing. So, therefore, increment of the strain ratio, incremental strain ratio can be predicted this positive minus 1 is to minus 1, that means one can be expand, another direction it can contract also. So, for this ratio is applicable in case of the uniaxial tension, but if a biaxial tensile, then we can see the biaxial condition, the sigma 1 sigma 2 equal to sigma bar, same, this is the value, and sigma 3 equal to 0. So, the ratio can be, incremental strain ratio can be different. Similarly, for plane strain condition, and for in this case the d epsilon 1 equal to d epsilon, the increment in other 0, and d epsilon 3 equal to minus d epsilon. If we follow and that follow this continuity equation, this d epsilon to 3 using this 2 equation, then we can reach this ratio, the stress ratio can be 1 is to half is to 0. That means, the one direction magnitude of the stress is half double of the other direction, and then other point, that is stress does not change basically. So, this way we can make the limit or deformation or restriction of the deformation or strain one particular direction, the principal stress component, because this d epsilon 1, d epsilon 2 and d epsilon 3 indicates the principal strain component. Now, what we can incorporate the strain hardening, what do you understand by strain hardening in case of this stress model also. So, therefore, bond Mises yield function only decides the explicitly mention the models of the strain hardening or how to yield evolves during the straining process. So, bond Mises yield functional form decides the shape of the function, but what we can evolve, that also can also be here. Also we can see that already explained this way also, because this is the function for f1 and this is the f3 for example. So, that means this is the functional form, but same functional form, there is no change in this thing, only the parameter sigma bar is necessary to describe the yield surface. It means that we represent k as a function of sigma 1 sigma 2 square dot dot. So, now this k, or we can say the k is equivalent to sigma bar square equal to half of sigma 1 minus sigma 2 square other condition. So, now this sigma bar can be changed effect of the strain hardening. So, it means that this is the first yield point, the strain hardening effect means this is the yield point, though we can say that it is a sigma 1. Now, it can be the sigma 2 strain hardening, it can be sigma 3. So, therefore, it will be following this curve, and but all this analysis of following this curve, but it will be in the incremental mode. So, that was that we will be able to evolve this yield surface and taking care of the strain hardening effect. Okay. So, kinematic hardening, this isotropic hardening on the single parameter sigma bar is isotropic hardening, means the shape remains the same, that it is evolved the same shape, but magnitude, this magnitude can be different, but following the same functional form in this case, that is called the isotropic hardening. So, equivalent way it is evolving for all the direction sigma 1, sigma 2, sigma 3. Now, if kinematic hardening means the yield surface size and shape remains the same constant, but the location translates according to the current stress. For example, this is the functional of the yield surface, but it remains the same and size remains same, but it translates the center point from here to here. This is the second one, it translates other point, third one. So, it means there is a yield surface and shape remains the constant, but it translates according to the state of the stress. So, this case is very much interesting in case of the when you considering the Bausinger effect important, or there is a abrupt reversal of the strain path. For example, suddenly there is a reversal of the strain path from tensile to compressive load. In that cases, maybe kinematic modeling is important, but actually in practical in the welding process problem, we normally use the isotropic hardening, that is more easy to understand and easy to implement also, but in actual practice we can use the combined hardening model also than isotropic and kinematic hardening. In these cases, model becomes more complicated, the plastic model, then you need a lots of parameter to be defined. So, this way we can differentiate in general we can understand that what is the isotropic hardening and what is the kinematic hardening. Now, if we look into overall this thing, different strain hardening, plasticity with the strain hardening effect, definitely we are considering the elastoplastic material and we are assuming some strain hardening effect is there definitely in this particular material, most of the engineering materials. So, if we assume that it is a ideally plastic material, then simply this functional is as a sigma ij and sigma y, one constant yield value for this particular material, because ideally plastic value, if you remember, this is the strain and this is the stress value. So, ideal plastic is the follow this way also. So, therefore, this yield point is constant in this case. This needs to solve, or if you want to find out the law these cases, in ideally plastic we have to follow this kind of expression. Isotropic hardening, we can use the f sigma ij in terms of the state of the stress in a particular point, and the remaining part, this other part is the sigma y. Sigma y means the yield stress value, but that yield stress value is evolving with respect to the plastic strain. For example, in this case it can be like that, this way also. So, that yield point value is the strain hardening effect, the yield point value is the incremental mole, is the updating in this case. So, therefore, the sigma y, the yield value is a function of the plastic strain. So, definitely we are talking the deformation happening in the plastic zone only. So, with the different plastic strain value, the yield can vary also. So, this way we consider the elastoplastic material, and even if we consider the isotropic hardening. So, that means we are not changing this expression, that it is a function of only sigma y state of the state in terms of the principal stress sigma 1, sigma 2, sigma 3, but this continuously changing this parameter this. But kinematic hardening, if we consider kinematic hardening, this we are not, there is no change in the yield point value. So, same yield point value, but translates the position the shapes in. So, that translation can be takes care of this thing, a sigma ij and alpha ij is that parameter, what way the translation from happens this in these cases, and it's can be a function of the plastic strain, but this remains constant, same value. So, in this functional form the kinematic hardening effect can be represents, and combining these two. So, this is also there, and both this yield stress also evolving, combining these two we can get that isotopic and kinematic hardening rule it is possible to apply during the plastic deformation of a particular process. Now, what we can apply the hardening rule application in this particular this stress analysis of welding process. So, initial yield stress is the value this thing, the sigma y is a function of plastic strain. Initial yield stress value is this one, and that this maybe you can say something like this, this is the initial yield stress value, this is corresponds to sigma y 0, and then further as a function of the plastic strain the yield point is basically yield point actually varying. So, that yield point is varying, the this is the slope, this represents the slope, local slope at this particular point, represents the slope at this particular point, the slope into the plastic strain value that represents the increment, and then it indicates that the incorporating the hardening law, then we normally represent the yield point or yield stress value that also evolves with respect to the different strain value. For example, this is the one incremental strain value d epsilon 1, then this is d epsilon 2, something like that, the incremental strain value. So, therefore, with the increment of the strain further straining the yield point also changes, and we consider the yield point changes as a function of the plastic strain, and this is the, we can simply add, this is the initial value this thing, and then gradually incremental value can be represented like that, the slope into the plastic strain that indicates this thing. Increment of the stress within the elastic limit can be represented only the following the Hooke's law, E into the increment of the strain. So, this increment within the elastic limit, this is the increment of the strain, but within the elastic limit the increment of the strain can be done on one single step, such that this is the increment of the stress, this is the slope basically Young's modulus, and that indicates the stress value, increment of the stress value only single step which is following in case of the within the elastic limit, because within the elastic limit the stress is proportional to the strain. So, you can use this relation, but relation during the plastic loading, then incremental of the stress, increment of the stress value is maybe you have to consider the slope or maybe modulus, the elastoplastic modulus, and the increment of the strain value within this zone. This elastoplastic modulus can be a function of the both this thing, the Young's modulus, and the plastic modulus itself. We can see this also. For example, this is the particular situation, this is the strain value and this is the stress. Now, one particular point is this thing, this is the increment of the stress value d sigma, and this is the increment of the strain value. So, now we understand that in a elastoplastic the total strain is the consists of the elastic strain and consists of the plastic strain. That indicates the total strain any during the deformation. Some part will be the elastic and some part will be the plastic. Even why it is considering like that, even if it is a plastic zone also, if it is a elastoplastic material, we remove the load also, some elastic recovery will also be there. So, therefore, total strain we will be counting combination of the both elastic strain as well as the plastic strain. Now, this elastic strain can be represented the same increment of the stress d sigma by Young's modulus, this elastoplastic maybe in these cases EP, and then if it is the elastic strain, we can see the same amount of the stress is correspond to the E d sigma by E, and in case of the plastic strain this is also d sigma increment of the stress, and we can take the modulus of this local modulus plastic modulus, and that can be EP. So, therefore, if we combine this thing 1 by EP elastoplastic 1 by E plus 1 by EP. So, from there we can say the elastoplastic modulus can be calculated by combining the only plastic modulus as well as the elastic modulus both, and then we can reach from here to this expression. So, therefore, we can see the special case of the perfect plasticity. So, if it is the perfect plasticity, then the plastic strain equal to modulus of plastic strain equal to 0 in that cases, then it will equal to the E elastoplastic will be 0 in this particular case. So, now in a elastoplastic analysis, that depending upon that the stress state, whether it is within elastic zone or the stress is within the plastic zone. So, therefore, increment of the stress can be calculated the proper modulus in this case. For example, within the elastic zone, then we use the Young's modulus, or if it is a plastic zone, then we consider the elastoplastic modulus, and then we estimate what is the increment of the stress in case of the elastoplastic material. If you assume the material behavior as elastoplastic, we can see the hardening law application. In this case, we can see the thermoelastoplastic model, and it is a bilinear isotopic hardening if we consider in this particular case, and this is the one simulation we have done in case of the stainless steel. So, laser power 25 watt and fiber laser and thickness 100 micrometer. In that cases, if we do the stress analysis, then we need to generate this kind of the stress strain diagram, which is need as a input to the model, because this model you can see this model can be this thing as a function of the temperature. For example, at the room temperature, this part indicates the elastic and this part indicates the plastic deformation part. So, elastic part and plastic deformation, we can say that bilinear, and isotropic hardening, if we follow isotropic hardening, that means this hardening effect is there because it is not exactly the horizontal. So, the slope represents some hardening effect is there in this particular material behavior. So, in this case we consider the bilinear isotopic hardening, then this kind of the data is required to the input to the model to represent, to define the stress strain diagram but this is a simplified way, because the plastic deformation we can consider as a linear curve. Then in that cases we can say the bilinear isotopic bilinear hardening in this case, and this we can see that as a function of temperature 293 Kelvin room temperature, this is the curve, and similarly the lower than this room temperature at higher temperature, this value actually changes, the magnitude of the changes, and then intermediate value any other temperature, then is simply interpolating the data is required from this stress strain diagram. So, it means that first thing is that elastic part is need to define this is the yield point, and then remaining plastic deformation part plastic part also be defined, but that plastic curve can be represented in the is a simple linear curve can also be possible, and that is easy to implement to define or easy to implement in this particular analysis, the stress analysis model. So, thank you very much.